This time, let's try to prove some properties for modulus of complex numbers. We know that the modulus of complex numbers corresponds to its distance of a complex point, or equivalent to the absolute value. So here, we're going to show that the modulus of a product of z sub 1 and z sub 2 is just equal to the product of their independent modulus. So to illustrate that, of course, let us try to illustrate these two with representations of complex numbers. Let's say this is a plus bi, and for your z sub 2, it's actually c plus di. And then let us not forget that the modulus of any z, where let us say it's x plus yi, I would like to use a, but these as they are already represented here for z sub 1. This is actually equal to the square root of the square of the real part and the square of the imaginary coefficient, or the y. So for this to be true, let's try to solve first the product of z sub 1 and z sub 2. Okay, so I believe let us try to start with the proof here. Yeah, we can or we can start here with the proof, but I will not be using any words here, or just like statements. So here is actually the product of a plus bi and then c plus di. Using the FOIL method, we'll get here a c plus a di plus b ci and plus b di squared. So that's I squared, because we have two i's here. And take note that if I is equal to square root of -1, then I squared is the square of that square, sorry for that, -1 square, that's actually -1. Hence, this will become negative in its sign. So you will have here AC minus BD plus, factoring I, you will have AD plus BCI. Let's try to regroup the first two as well. AC minus BD plus AD plus BCI. I would like to use grouping here so that, just like in our first two example where A and C are our real numbers or real part, this would correspond to the real part as well. And if this x is the real part of z, we're going to take the square of the entire expression for our modulus. In short, at the same time, for our y here, that corresponds to this expression. Okay, so let me move further here. As we have the modulus of the product of z sub 1 and z sub 2, that's actually the modulus of AC minus BD plus AD plus BC times I. Again, this would be our real part. This is the imaginary part, where this is our imaginary coefficient. So it's actually, let me use another color here, it's actually equal to the square the square root of the real part AC minus BD, take the square of that, plus the square of the imaginary coefficient AD plus BC. Our goal is to make sure that from this we will end up with the product of their individual modulus. Okay, so let's try to manipulate this, and hopefully we could arrive into the product of their independent modulus. Talking about z sub 1 and z sub 2. So by simplifying this, you will have the square root. So you will have a squared c squared. Okay, or let's do it step by step. AC squared minus twice AC times BD. Okay, that's actually how we square a binomial. Or let me move this a little bit closer here, because I need to work that on both binomials. Then you will have here plus the square of BD. On the other side, plus the square of AD. Then plus twice AD times BC, and then plus the square of BC. Then, of course, this would become A squared C squared minus twice ABCD, simply rearranging the coefficients alphabetically, and plus B squared D squared. Then, plus A squared D squared, this is plus twice ABCD as well, and then plus B squared C squared. I would like to take your attention in these two terms. They're actually just opposite of one another, so we can just simply remove them, thereby making our next expression equal to A squared C squared plus B squared D squared plus A squared D squared and plus B squared C squared. Okay. Take note, again, our goal is to have a situation like this, so we can see a product of their independent modulus for these two. Okay, so A and B, if we're looking at this, should be together, and C and D should be also together for their separate modulus. If that would be the case, I would like to rearrange the terms on our radicand such a way that I could factor A squared and B squared. A squared C squared, I'll be writing this first, plus A squared D squared, then this one B squared, or I could have B squared D squared plus B squared C squared. As mentioned, I can now factor the common. A squared has been factored. Okay, this is actually C squared plus D squared. Then if I will factor B squared here, that's D squared plus C squared. We know that this could be interchangeable, so pardon me if I'm going to interchange them here, even if in the previous they are not interchanged. Nevertheless, they will be the same. Hopefully you've been following. I'm doing that so that I can also factor this as a common. Is equal to the square root, factoring C squared plus D squared. What remains in our first term is just A squared, and for our second term is B squared. Okay, now let's stop here for a while. Let's try to predict what should happen if we're going to stick with these ideas. I know that this should not be the process, but if this would be the goal, it should also help us to foresee what is our intended target. Take note that the modulo of z sub 1, being z sub 1 given here, a plus bi, is actually the modulo of a plus bi, which will give us a square root of a squared plus b squared. As for z sub 2, that's actually the modulo of c plus d I. It's the square root of c squared plus d squared. I'm looking into this because you can see that both of these radicands can be seen inside. Then that would help us going further. In short, we can separate them because the property or the law for our radical expression, if we have products on our radicand, simply separate them into separate radicands. C squared plus d squared, as long as the radical expressions will have the same index as the original. Okay, so that's actually a squared plus b squared, which gives us a result, okay, of the modulo of z sub 2, because that's our z sub 2 here, times the modulo of z sub 1. And since multiplication is also commutative for complex numbers, simply rearrange them, modulo of z sub 1 times modulo of z sub 2. We have arrived at our intended target, showing that with all of this from here, we have shown that the modulus of the product of two complex numbers is just equal to the product here of their separate modulus. And we have shown that using this idea of proof. Okay? Hopefully it's clear for this video, as we will have another set of property in the next one. Thank you very much for watching.